Oh, hello. Good afternoon, everyone. Whoever bothered to come, I thank you very much. I know we are on a Saturday and having you guys full disposition to learn something is really great. Really pleased to be here to be talking to you about today's topics, which is the perceptron and gradient descent. So I'll be going through a presentation on these two topics. It's quite a lot of ground to cover. I will leave the chat open. Any questions you can ask at any time, but at the end of the webinar, I do intend to leave some free time so you can ask any questions you have. It is a nice topic. It is an interesting topic. Basically, we're going to talk about the basis for neural networks, basis for what has been the big fuss on machine learning in recent years, which is deep learning and these new techniques, which are really revolutionary and promise to deliver a greater capacity for problem solution. If you go through a few of Apple's latest presentations, you see that they always talk about something about deep learning. They say we're actually using deep learning for this or for that, and so you can see how the fuss is and how it has become a buzzword, even though the people watching Apple's presentation probably don't know anything about deep learning. They just heard the word somewhere, and Apple thinks that it is important to tell them that that they are using it. And actually, the deep learning models actually do make a lot of sense. They help a lot by improving the systems like speech recognition, the translation. Actually, if you remember how bad the Google Translator was a few years back, it was because they were not using a deep learning model. Now they are. So in the past, I believe 2 years or so, they switched to a deep learning model, Google's deep learning model. So improved quite a lot, and this is the basis. I mean, deep learning seems to be complex or something like that, but it's just a few steps after you learn the basics. So let's jump in and start talking about the perceptron. So where are we? Here's the presentation, and let's get going. Sorry, I have to share my screen and restart the presentation. So now I'm sharing. Hope you guys can all see. And here we go to the presentation. Perceptron and gradient descent by me. So let's go. So what is a perceptron? The perceptron is a type of neural network, a mathematical model actually invented in 1957. So it's been quite a few years, by a guy named Frank Rosenblatt. And what it is basically a linear classificator. It solves just linear problems. We're gonna see in a bit what is a linear problem, what is a non-linear problem. And what is important about the perceptron, it is the basic cell for the neural networks. That's why we have this MLPs. Neural network, when you see MLPs, just mean multi-layer perceptrons. It means you use a multiple layer of perceptrons stacked against each other, and to solve a problem. So this is your neural network. It just multiple layers of perceptrons. The perceptron is just the individual cell, is just the one neuron, what we call a neuron. So this is the basis for a tribe of machine learning, and I'm referring to it as a tribe because I'm based on the research of a guy named Pedro Domingos. He's a researcher and he has a nice book. I recommend you guys to look for it if you haven't already. It is called The Master Algorithm. It's going to give you guys a lot of grounds on this basic machine learning algorithms, which he calls the tribes, like the connectivists, the evolutionists, the Bayesian, which means use the Bayesian theorem. What else? We have the symbolists, which use the decision trees. The decision trees you just saw. I mean, it is a very interesting topic because in each one of these was born from a different field. For example, the evolutionists come from evolution, from the study of evolution, and they believe in evolving a model, evolving a solution to any problem. You see that a lot on problems that are not possible to optimize through standard practice, like the traveling salesman's problem, which is a problem that's basically impossible to solve. But when you employ these techniques, you actually get very good solutions. You may not get the best solution because it is virtually impossible, but you get really better solutions. And what else? The analogies, which the master algorithm is the support vector machines. And you see this. I'm not gonna talk a lot about these different tribes because we are focusing on the perceptron and the connectivists. The connectivists believing the way through intelligence is by simulating the brain. So they believe in creating these artificial neurons, which now we know they are perceptrons. And by the connection and training of these neurons, we should achieve something that resembles intelligence. So this is the artificial intelligence. I mean, the connectivists have been, like I said before, they have been on a hike lately because of deep learning and how much these models have achieved lately. So they have been really the guys. Actually, they have been more important than anyone. They have getting a lot more attention than everybody else. But I mean, these other tribes actually still work, and they actually have good members, and they have good solutions, and they have good models and good startups running through these other algorithms. But this is the basis for the hostess algorithm lately. So let's get going. Now we know what the basis of our perceptron is. It's a mathematical model created in 1957 by a guy named Frank Rosenblatt, and it performs linear classification. I'm going to see what is linear classification in just a bit. And it's the basic cell for neural networks. Just knowing that it is the basic cell, just say how much it is important. If you want to really understand neural networks, you have to understand the perception. So this is a neuron. This is what we're trying to simulate. The neuron receives impulses from different neurons, and after these pulses, these electrical pulses, reach a certain threshold, the neuron itself is going to activate and send a signal forward. That's what we're trying to simulate, a way to um, have inputs that will give you some sort of stimulation, and after make some activation based on this impulse and send this signal forward. This is perceptron. I apologize for my drawing. Basically, I'm not a very good cartoonist, as you can see. This is obvious, but this is what a perceptron is. What is a perceptron? Basically, a perceptron is this guy in the middle, and it is the result of the multiplication of the X matrix, your matrix of features, by some another matrix, and we do the sum of this multiplication. We actually doing the I'm gonna shift to here so I have a mouse. So basically, what you do, you're taking the matrix of features, which means the axis here, and we're gonna pass in then multiplying by a feature matrix, by a matrix. I'm sorry, by a matrix of weights. We're summing this multiplication, multiply x11 by w1, multiply this guy by this guy, this guy by this guy. We add everything, and then we perform an activation function over the result. Here I'm representing the sigmoid function, which is the most common. I mean, there is a lot of functions. I believe they are all stated. You can find them easily on the internet by the different functions. And there is still research on this topic. Of course, there is research on this topic. But what is important is that this function must have a derivative. You guys, it's a little bit beyond the scope of this webinar. Actually, could go on forever talking about this, but this is what it is. You multiply the features. Here I'm multiplying a single sample. Each this is the feature matrix, and each row is observation. You have one observation here, and the second observation here, and you could have many more here. What you do is you take one, multiply by the weights in the matrix of the perceptron, and you add them together, perform the activation, and then you do the training. Why you do the training? Because the way you initially obtain these weights is by random. You just when you initialize the perceptron, you have a matrix which is composed by random weights. So you do a passing through these weights, and you see how it does, and you do the training by adjusting this, going back and adjusting this weight. This is the perceptron, and now go to the training rule. The training rule simply is that is what we're taking is we're taking the weight and adding by the weight by this term, which is delta W. Delta W actually equals to the learning rate multiplying by the target. We have the target here. We have the sample. We have its target. This target minus the output of the perceptron. It is represented by an O, but it's the result of taking this sample, multiplying by this weight, doing the activation, this, and this is the output. The O is the output of doing this. Take a sample, multiply, add this multiplication together, perform the activation function on the results, and you get the O. And that's how you calibrate your rates, which initially are random, so you can pretty much expect a random result. and after training, you should expect to have solved the problem. You have the input here. It is also in the multiplication calculation is W, and you take W by it, add to this correction fact, this corrector term, which is doing the correction, and you get a new W, and you get your new weights matrix, so to say. So what is a linear problem? I say this solves linear problems. And what is a linear problem? Well, let's go back to reproducing the presentation. And here we have a linear problem. A linear problem is a problem like this, which is solved by a linear separator. In this case, we're talking about two-dimensional space, so we have a one-dimensional line separating the two samples. In this case, we are classifying class 0, which are the red dots, and the class 1, which are the green dots. Anything to one side of this line is classified as a red dot, to the other side has a green dot. And this is a linear problem. This is all the perceptron can do. You only can solve linear problems. So that's the problem. That is a problem. This is a problem because we have this XOR problem. XOR means exclusive OR. Basically, let's look again what it is. A non-linear problem. Let's look. This is a linear problem. You can separate by a single straight line. This is a non-linear problem. You cannot separate by a single straight line. You have to use a curved line. Maybe you have to use a circle or something like that. And the perceptron cannot do this. So this actually generating quite a lot of disinterest by the perceptron back then when it was invented, because all it can do is linear problems, and most problems are non-linear. And what can we use this thing for? I mean, if it's not going to be able to solve most problems, the problems of interest, why would we care for this thing, for this invention? And one of these problems is the XOR problem. Here we have the XOR problem. Basically, is the exclusive OR. So, which means is you have two variables, x1 and y. The output will be one. One of them is 1. One of these variables is 1, and the other one is 0. If both these variables are 1, we have here it's going to be 0. If both of them are 0, it's going to be 0. But if y is 1 and x is 0, it's going to be 1. And if x is 1 and y is 0, it's also going to be 1. As you can see, we cannot use a single straight line. You can actually try if you want, but there's no line that can separate perfectly these samples. You're always going to have a green and a red in one side, and that's why this problem is non-linear separable. You cannot pass a line through here. Imagine a line passing through here. It's gonna leave this green point with these other two dots. Right here, it's not gonna work. Right here, it's not gonna work. It's not gonna work. And even if we do something like a curved line, which means we're not using a linear separator by now, still we cannot solve. But thankfully, this problem has been solved actually quite a few years ago, by something we call the covert theorem, which is the covert theorem. It is a theorem named after a guy named Thomas M. Cover, who stated it in 1965. So keep in mind that we have the spectrum invented in 1957, but the way to solve this nonlinear problem was only invented in 1965. And what is stated is that we can actually separate this problem just by transforming it into a higher dimensional problem. Here we have two dimensions. We have x and y. Basically, we have a high probability, is actually what the theorem says, of solving it if we cast it to a three-dimensional space. If when we would have x, y, and z. And I'm actually gonna show you this right now. I'm gonna have a very good video presenting. So imagine you have this example. This problem is actually solved the XOR problem, which is very common in literature, and was actually solved by this way. So I'm gonna play to you an example of how this actually works. Was you basically take a problem that is in 2-dimensional, cast it for 3-dimensional. If you have a problem in 3 dimensions, you cast it to 4 or more dimensions. So yeah, you can actually cast it to 2-dimensional problem to a 3-dimensional problem, to a 4-dimensional problem, to a 5-dimensional problem. What matters is that you cast to a higher dimensional. Not you cannot cast this to a 1-dimensional and expect it to be solved. You cannot not cast a 3-dimensional problem to a 2 dimensions is expected to be solved. So let's show how it works. So I actually found this video and is actually quite good for showing how the problem is solved, how it actually works. This is a small video. So see, now we're casting, and once again, first we have the problem in 2 dimensions. You cannot pass a single straight line. You could pass a circle, but it's not a straight line, of course. So now that we have in 3 dimensions, we can separate it by a plane. So that's what is important. To separate it becomes a plane, becomes the next dimension. For example, the separator was a line on 2 dimensions. Now it is a plane. If we cast it to 4 dimensions, it is going to be something higher. But the thing is now, with a linear separator, we managed to solve the problem. So this is what the covert theorem is. It is actually also basic for neural networks. I don't believe it is in your material, but thankfully now you have it. So let's look at an example of a multi-layer perceptron. This is a conventional neural network because it has 3 layers. The conventional neural network has 3 layers. It always has 3 layers. And deep learning actually means that we add more layers. So it is no longer a conventional neural network. It becomes a deep learning model, and we add 4, 5, 400, 300 layers. 500 layers is something common to these networks. Google actually had a project when they had thousands of layers. So this is a conventional network. As you can see, you have a 3-dimensional problem, and we're actually casting it to four-dimensional problem to 4 dimensions. So you have these four neurons instantiated. Here just means that your feature matrix. This is a feature matrix. This is a matrix of weights, and you're gonna cast it again and add this to the to the activation in each one of them, add them together, and you get to the results. This is a 3-layer. This is the output layer, and you get to output after doing all these operations of multiplying, activating, adding the activation, and activating it again, running an activation of the result of these neurons, and you get this output layer. So Here, what's happening behind the scenes, you have, I'm taking one sample as an example. It could be any samples, as you can see here, any rows by 3 columns. Your weight matrix must have three rows, because this is how the matrix multiplication is defined. If you remember a little bit of algebra, to multiply these two matrices, you need to have this guy has to be equals to this guy. The result will be this guy and this guy. You have this number of the result. You have this number of rows and this number of columns given here. The multiplication by this one guy by this guy is actually 1 neuron. This guy by this guy, this row by this column is the second neuron. This row by this column is the third neuron, and this row by this column is the fourth layer. If I wanted to have a four-dimensional, if I wanted to add another neuron, it would actually be easy. I'll just have to instantiate in my matrix in such a way that I have another column here of three rows, and then I'll get another neuron. If I want one more neuron, just add another column, and this is how it works. So as you can see, the perceptron is just the multiplication between matrices, between the feature matrices here and the weight matrices, which is initially instantiated as a random matrices. I mean, it has just random numbers there, and then it is calibrated after you compare the final result by the expected result. So as you can see, it's one of the things I had problems by understanding, because I could not get my head around the fact that this is not an entity. This is just a multiplication operation followed by an activation. So this thing is just multiplying these guys by this guy. This guy right here, the first one, is just I multiply this guy by this guy and do the activation function. Could be the sigmoid function, could be the ReLU function. We actually have a good material on why we use one or another sometimes. And there's many more functions, but this is what the perceptron is. Each one of these cells, these neurons, each one is a perceptron actually. These 4 perceptrons, as you can see, this is a neural network composed of this number of perceptrons. And this is just the feature matrices. So I'm going to iterate, take this, multiply by these guys, multiply this by this, and this by this again, this by this by this. And I'll get from the activation function on this guy, this guy, add them together again, perform an activation function again, and get the output, compare, propagates my error back here. I actually don't have time to explain backpropagation right now, because it would be a topic in itself, but we have good material on your classes when you actually reach the time when you will be using backpropagation. And that's it. This is the perceptron. And now you have to move to gradient descent. I'm gonna look through if you have any questions. Do you have any questions? No, we do not have any question. But I'm still open after the webinar if you guys want to ask any questions. I'll be happy to answer. But quite a thing, isn't it, when you get to know this? This is not an entity. This is just a result of the multiplication between matrices and an activation function performed after these results. That's it. We don't. It's interesting, isn't it? Now we get to gradient descent, finally, which is the last topic of today's webinar. And another topic of great interest to you, to everybody who's interested in machine learning. And what is it? This is a technique which minimizes the error. And gradient factor is just a fancy word. Gradient descent is just a fancy word, actually. And we use a gradient vector, which is a fancy word for using the derivative. That's why you need the function is to be. You need to be able to derive the activation function. The activation function has to be a function which has a derivative, and this is actually where you're going to use the calculus. Your calculus knowledge, but don't worry, you only need the concepts. As I said before, in machine learning, in data science, we don't usually use those complicated functions unless you are in academia. But on the industry, you actually interested in solving the problem, not doing research. You may use these complicated derivatives, find these complicated integrals, but only if you are interested in going through the academia and in doing research. If you are interested in doing the implementation, actually going and implementing these models, you're probably never gonna use it. And I mean, maybe even in academia, sometimes you're not gonna use. I mean, most of the times you're not gonna use those advanced calculus. That's why I said you're not gonna use it. You are very, very unlikely to use any of those. Only of those things you learn in your calculus classes. Just the concepts, which is important. So you know that derivative is the rate of change. Simply like that. That's all you need. Keep that in mind and you'll be fine. So the gradient factor, it is something that points to the direction of the greatest positive variation. Since we're trying to minimize, we're trying to go in the opposite direction, just multiply by -1, and we get the n, we get the gradient that we're trying to minimize. So here is what we're doing. Here we have a function y, as you can see, it's just a two variables function. Y as a function of x. You have x equal y equals to x to the second. So and here we have what would be the gradient function, which is just be the derivative of y with respect to x. Simple like that. This gradient vector identified by this upside down triangle would be just just derivative of this one variable, because we only have another variable. And what we're trying to do, we do this. We get to the initial weights here, and then we minimize until we reach the global minimum. Well, in this case, we can reach the global minimum, but most of the time you're not going to reach the global minimum. We'll get to that in just a few seconds. Don't worry. And since I'm talking about two-dimension, what would happen if we had a three-dimensional? Simple like that. We'll have z equals to x plus y. And now your gradient vector would be this guy here that I identified as a v, because I do not have the proper symbol, but this is the symbol for the gradient vector. Just the derivative of z with respect to the first variable for one element, and the second element would be the derivative of z with respect to y. So since we have z as a function of two variables, the gradient vector has two components. As you can see, this is not the function that represents this surface. I don't know what the function for the surface is. It's just took it from the internet and made something easy so you guys can even calculate the derivative. I mean, when we derivate z with respect to x, we just care about the x variable. So we ignore y, anything that doesn't have x. So derivating x, we get 1, and this one, derivate y, forget about x, would get 1 as well. But I mean, it's just an example of what the gradient vector is. And this is the guy we use to, as I can say, points. When you check this, is actually pointing to up, to the direction when you're gonna increase it this the most. But we actually want it down, just put the minus symbol here. And anything that is compute, we take the negative of it and we use to optimize your model. So what be this guy here? Simple, just derive this function with respect to x, and the derivative of x elevated to the second power, it is 2x. Simple like that. I mean, if you remember the basic derivative rules, so you're not going to use that. I mean, just giving an example. But what we're usually going to have as a function to derivate is the sigmoid function, which the derivative is sigmoid times 1 minus the sigmoid, and we're not going to use it because the framework, the sklearn, PyTorch always have these things already implemented, because there's no reason for making you to compute something that is fixed. The derivative of the real function is something fixed. The derivative of all these functions, of course. So you don't even have to know how to compute the derivative. You just need to know what a derivative is. And I mean, I just remember how to compute this, but most of the functions I also don't remember, so I don't even need to look. It's just implemented for me. Now we're talking about the learning rate, and I said this guy here needs to be something small, because this is what it does. I mean, if we are sitting here and we actually get the gradient descent, the gradient vector pointing somewhere down here, and we use a very, very high uh, um, learning rate, we may end up here. Imagine if we end up here. Or imagine if we just start here and it send us down, and we just go down, 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 but while our learning rate was too high, and we end here. And then we take the get here, and we take the gradient factor again, and it will send us back down. But then again, well, our learning rate is too big, so it could come all the way down, up again. We do the same thing, it's going to point down again. Yeah. As you can see, this model is never going to converge, and this is why we use a small learning rate. And it's gonna get here, get here, get here, and it's gonna get to this point, and it's never gonna leave, because we actually achieved a minimum. I'm not sure this. You cannot say that is the global minimum. We're gonna see why in the next slide actually. And I actually say you need a small learning rate, but it actually has to be a good learning rate, because imagine if it was too small, and you go from here to here, and then from here to here, and here to here. Or maybe we are moving even less, and it will take us forever until we get to convergence, to a local minima or global minima. We're not good, but if you have a good calibrated learning rate is actually comes in the usual sizes 0.01, 0.1, 0.05. You actually try these numbers and see how good it gets, but this is actually the scale of this learning rate term that I just showed you guys. Where is it? Right here. and this guy will calibrate the size of your increase or decrease in your for your calibration. Too big, you do this, and you never converge. Too small, you go from small, very small, very small, very small, and maybe you won't get to converging time. Maybe it will take you, I don't know, hundreds of years to get to the convergence. If you get it too small, imagine that you somehow want to get 0.00000000001, you never get to converge. This is not good, and that's why you need to choose a proper learning rate. This is covering the material. I'm just showing you guys for the sake of interest, for the sake of showing something interesting, and because I can. So let's move on for local minima versus global minima. So as I was saying, the gradient descent we just point to the direction of the of going down, make you go down. But when you reach this point, imagine that you start like this guy. You're actually trying to go down a mountain, blindfolded actually, and you reach a point where you cannot. All the ways are up. I mean, you have no way in a function to know if you are at the minimum or the global minimum. I mean, in this case, the global minimum is here, but we have since this thing goes on forever, we have no guarantee that there is not a smaller minimum if we move beyond this guy, beyond this peak, and we may find a global minimum that is much smaller, and there is no way we find a global minimum actually, and that's actually not a problem. I mean, most of the times the local minimum will do just fine. I mean, most of the times we actually want the local minimum because the global minimum may signify that we are actually we actually overfitting the model. We're actually getting to reduce the error too much on our training data set, and we're gonna overfit the model. I hope you guys all went through the overfitting material, and as you can see, something we do not want to happen. And being at the global minima actually could mean that we are actually overfitting, and that's not good. So almost always, if not always, a local minima will suffice. And if you want to suffice, you have techniques like like uh, like inertia, which would mean that like we would actually get here and go all the way and find another minima, but it is covered in your material, and I would take too much for us to cover it here and will not be good. I mean, we almost out of time right now. I mean, this webinar is taking more than 42 minutes already, and I don't want to take too much of your time. And this is just something I wanted to bring it for you, that most of the times you're gonna get to a local minimum. If not always, you're gonna get to a local minimum, and that's fine. I mean, you just have to be the best local minimum you can search for. Maybe you got your local minimum that is not actually solving the problem, and you need to amplify the the searching space by using some of these techniques which are covering your material, and you actually should look online for more resources, for more papers and articles on this. But that's not a rule. I'm gonna anticipate this for you. There's not a rule on how to always find the best. There's not a mathematical formula, and it is basically trying. You just try to solve the problem, and you see that it does not solve well. You find a technique you apply, and it maybe function and maybe not function. Maybe your model gets worse. And this is how we do. Is pretty empirical. You may think, and yes, it is. It is pretty empirical. And all the field is pretty empirical, and even machine learning, data science is all. There's a lot of parts which are not actually covered in by a mathematical formula, and you have to try and see what's best. So let's move on to let me look again. And I'm sorry, this is not from you guys. I'm looking again. The chat is open, no questions, and I'm gonna look through this through our the final topic I want to show you, which is the SGD. When you are implementing your deep learning models, you see that you are not doing gradient descent. We're actually doing this stochastic gradient descent (SGD). When you actually use the model, the PyTorch model only has this SGD, and what it means is that you're not using a deterministic approach, but rather a um, a stochastic approach, which means that you're not gonna get this straight line like this. This guy is the would be the deterministic approach, and this guy is the stochastic, which means it doesn't get always to the best place. You see, you need a lot more interactions, and the reason why we do this is because gradient descent is very expensive and very expensive, really. I mean, and the stochastic approach actually is gonna have a trade-off. I mean, we're gonna gain speed by calculating the gradient vector, but we're gonna lose precision. We're gonna lose it's not gonna be such a good estimator, but it is good enough. And in real case scenarios, the stochastic approach actually works, and that's why you're gonna be using SGD on your second project for optimizing your model on your second project. And this is what SGD stands for that you're actually doing gradient descent. You're not doing the deterministic one, you're doing the stochastic one, and that is okay. That is actually probably the best you can do. Maybe the deterministic approach will never converge because it'll be too slow. Will take months maybe to converge. Will take while the stochastic approach will get you there in a lot faster. And I mean, we're taking more iterations, but each iteration is much faster, and we'll get you there to the same results and such a smaller cost. And in real case scenario, this is good. This is good. This is what we use, and this is what PyTorch uses. So by this time, I'm pretty tired by now. I'm guessing you all are tired because there is such a complex topic. And I bid you. No, I don't bid you goodbye right now. I'm gonna go back to the. I'm gonna minimize this. Go back to our transmission. I'm gonna stop sharing the screen. And okay, now if you guys have any questions, anybody has any question, just say something. Be glad to answer. Or maybe you wanna leave it to the to our Slack channel. It's also fine. I'm not discriminating, but if you wanna talk about it live, I'm here right now. So nobody's gonna say anything. We're all fine. I mean, yeah, I understand that this may be a complex topic, especially if you're taking for the first time. Um, I guess somebody sent me a message. Hello. So I'm gonna finalize the webinar by now. Wanna thank you, Brando, for showing up. I wanna thank you, Vijay, for showing your interest in the webinar too. Anybody else who's watching, I thank you so much. Even if you're busy and you're gonna watch it later. And that's it for now. Goodbye.